We have already learned what machine learning is, how a model learns, the different types of machine learning, and the complete ML project lifecycle in previous videos. Now we are going to focus on something even more important, data. Because in a real machine learning project, the quality of your model is heavily dependent on the quality of the data you give it. Imagine I give you the world's most advanced machine learning algorithm. But the training data contains incorrect labels, missing values, duplicate records, biased samples, and information that wouldn't actually be available when making predictions. Do you think the model will magically fix everything? No. In machine learning, a sophisticated algorithm cannot automatically turn bad data into good data. That's why experienced ML engineers spend a huge amount of time understanding and preparing data. Machine learning models learn patterns from data. So, if the data contains the wrong patterns, the model can learn those wrong patterns. This creates a chain reaction. Bad data can lead to incorrect patterns. Incorrect patterns can lead to a poor model, and that poor model produces poor predictions. So, before asking which algorithm should I use, an ML engineer should ask, do I have the right data? Let's understand what data actually looks like in machine learning. A data set is usually a collection of examples or observations. Each row represents an observation. Each column represents some information about that observation. For example, suppose we are building a model to predict whether a customer will leave a company. Each row could represent one customer. Age, income, and number of purchases could be input features, and churn could be our target. The concept you absolutely need to understand are features and target. Features are the input information that the model uses to make a prediction. The target is what we are trying to predict. In this example, age, income, purchases, and login frequency are features. Churn is the target. During training, the model uses the features along with the known target values to learn a relationship between them. Data doesn't always look like a spreadsheet. We can have numerical data such as age, salary, or temperature. We can have categorical data such as city, gender, product type, or subscription plan. We can have dates and timestamps. We can have text, images, audio, and video. And the type of data we have affects how we prepare it and which machine learning techniques we can use. Numerical data represents quantities. For example, age, salary, temperature, and number of purchases. Numerical data can be continuous or discrete. Continuous values can take many possible values, such as temperature or height. Discrete values are usually countable, such as number of purchases or number of support tickets. Understanding this can affect how we analyze and pre-process the data. Categorical data represents groups or categories. For example, city could be Bangalore, Mumbai, or Delhi. Subscription plan could be basic, premium, or enterprise. Machine learning algorithms generally cannot directly work with these text labels as they are. So, we often need to convert categorical information into numerical representations. One common approach is one hot encoding. Suppose our feature is color and it can be red, blue, or green. We can create separate binary columns for each category. Red becomes 100, blue becomes 010, green becomes 001. This allows the model to work with categorical information numerically without implying that one category is naturally larger than the other. Dates and timestamps can also contain valuable information. But instead of simply giving the raw timestamp to a model, we can extract useful features. We might extract the hour, day of week, month, or number of days since a customer's last activity. This is an example of feature engineering, which we introduced in the previous episode. Text is another important type of data. Consider customer reviews. A review such as I love this product contains useful information. But a traditional machine learning algorithm cannot simply understand the sentence as a human does. We need techniques to convert text into numerical representations. Modern systems often use embeddings where text is represented as vectors that capture useful semantic information. I have covered embeddings in a separate video for which I'll provide a link in description. Go through it to understand more about embeddings, how text is converted into vectors and stored in DB. Images are also data. At the lowest level, an image is made up of pixels. Those pixels can be represented numerically and processed by machine learning models. Computer vision models can learn patterns such as edges, shapes, textures, and eventually more complex visual structures. Another important distinction is structured versus unstructured data. Structured data fits naturally into rows and columns. Traditional relational databases are a common example. Unstructured data doesn't naturally fit into a simple table. Text, images, audio, and videos are examples. As an ML engineer, you need to know what kind of data you are working with because the entire data pipeline can change depending on it. Data can come from many sources. We might get it from databases, APIs, application logs, transaction systems, cloud storage, or external datasets. In a real project, combining these sources can itself become a major engineering task. You have to make sure that the data is consistent and correctly joined. Now we come to one of the most important topics, data quality. Good data should be correct, complete, consistent, relevant, and timely. If a customer's age is recorded as 350, that is not correct. If 30% of the values are missing, the data set is not complete. If one system stores India as IN while another stores it as India, you may have consistency issues. And data that is accurate but no longer relevant to today's business can still produce a poor model. Missing values are extremely common, but there is no single solution that works for every dataset. We might remove some rows if only a tiny number are missing, and doing so is safe. We might use the mean or median for some numerical features. We might use the most common category for categorical data, or we might use more sophisticated imputation techniques. The important point is don't blindly fill or delete missing values without understanding why they are missing. Outliers are observations that are unusually far from the rest of the data. Suppose most customers are between 20 and 60 years old, but we suddenly see an age of 250. That's probably a data error. But an unusual value is not automatically wrong. An expensive transaction might be a perfectly legitimate transaction. So, an ML engineer should investigate outliers using domain knowledge instead of automatically deleting them. Duplicate records can also cause problems. If the same customer appears multiple times accidentally, the model may effectively give that example more importance. But again, don't automatically delete duplicates. Sometimes multiple rows for the same customer are completely legitimate. You need to understand what one row represents before deciding whether something is a duplicate. Another major issue is bias. Suppose we are building a model for a population, but our training data heavily represents one group and barely represents another. The model may learn patterns that don't generalize equally well to everyone. Data bias can come from how data was collected, historical decisions, sampling methods, or even missing groups. So, advanced ML engineering isn't just about maximizing accuracy. We also need to ask whether the data represents the population we are making predictions about. We discussed data leakage in the previous episode, but it's important enough to repeat. If we are predicting whether a customer will churn at 10 a.m., we can only use information available at 10 a.m. We cannot use the cancellation date if that happened later. If we do, the model gets information from the future. This can make evaluation look fantastic while the model fails in production. Often, we cannot use every possible example in the world. We need to create a sample. The sample should represent the population we are interested in. Poor sampling can create a dataset that looks fine technically but doesn't represent real world users. And then the model may perform well on the sample but poorly on actual users. This brings us to an important idea. Your training data is only a sample of the real world. If production data looks significantly different from training data, model performance can suffer. That is one of the reasons why data monitoring becomes important after deployment. Before training, raw data usually needs pre-processing. We may clean invalid values, handle missing values, encode categories, scale numerical features, and create useful features. The goal is to transform raw data into data that the model can actually use effectively. Some algorithms are sensitive to the scale of numerical features. Imagine one feature ranges from 0 to 100, while another ranges from 0 to 1 million. Depending on the algorithm, the larger numerical scale can influence the learning process. Techniques such as standardization or normalization can bring features into more comparable ranges, but scaling is not necessary for every algorithm. So, the pre processing strategy should depend on the model. An important mindset for an ML engineer is to think of data preparation as a pipeline, not a collection of random notebook commands. Raw data comes in, we validate it, clean and transform it, generate features, then send those features to the model. This pipeline needs to be reproducible and consistent between training and production. Before training, we usually divide the dataset into separate parts. Training data is used to learn the model. Validation data helps us make development decisions such as choosing a model or tuning hyperparameters. And the test set is kept aside for the final evaluation. The exact percentage can vary depending on the project and dataset size. But here is an important point, we don't always randomly split data. For time dependent problems, random splitting can accidentally allow future information to influence training. For example, if we are predicting future sales, we might train on older data and validate and test on later periods. The splitting strategy must reflect how predictions will actually be made. Before training any model, I recommend asking these questions. Is the data correct? Is it complete? Is it consistent? Does it represent the population? Is there leakage? Are the labels correct? And does the data correspond to the correct time period? These questions can save you from building a sophisticated model on fundamentally flawed data. This is the key message of this entire episode. Your model doesn't exist in isolation. The model learns from the data you provide. If the data contains systematic problems, the model can learn those problems. That's why data preparation isn't boring housekeeping. It's a core machine learning engineering skill. You can think about the ML data journey like this. We start with raw data, we clean and validate it, we transform it into useful features, the model learns from those features, and finally it produces predictions. Every step matters. Let's connect everything with our customer churn example. We may collect raw customer information from purchases, logins, and support interactions. From this, we create useful features such as days since last login, purchase frequency, and number of support tickets. Those features go into our model, and the model produces a churn probability. This is what data processing and preparation looks like in real ML project. You may hear people say that most of the work in machine learning is actually data related. The exact percentage varies by project. So don't focus on a specific number. The important lesson is that collecting, cleaning, validating, transforming, and maintaining data can take a huge amount of engineering effort. This is why advanced ML engineers need strong data skills. As you progress from beginner to advanced ML engineer, your questions should become deeper. Don't just ask which model gives me the highest accuracy. Ask where the data came from, whether it represents reality, whether the labels are trustworthy, whether there's leakage, what happens when production data changes, and whether another engineer can reproduce the entire pipeline. Let's recap. We learned about different types of data, features, and targets, structured and unstructured data, data quality, missing values, outliers, duplicates, bias, sampling, and data leakage. We also looked at preprocessing, feature scaling, and how data is divided for training, validation, and testing. If you remember only one thing from this episode, remember this. Data is not simply input that we throw into an algorithm. Data determines the patterns the model can learn. And understanding, validating, and engineering that data is one of the most important skills for an ML engineer. In next episode, we will take the next step and actually investigate our data. We will learn exploratory data analysis or EDA. We will see how to understand distributions, relationships, correlations, outliers, and hidden problems in a data set before we train a model. That's where we will start getting much more hands on with real machine learning data. Thank you for watching. See you in next video.